So if the number one electron drops down, so then does that become the plus or minus, or what is that?
The charge is more negative. The amount of binding energy is more negative. It's less energy the closer you get to the nucleus. The positions closest to the nucleus, these inner shells, are the positions where these electrons have the lowest energy.
So it's a +5 and it goes down to a minus.
Yeah, more like it's a minus something and it goes down to a bigger minus number.
Okay.
Right. So let's say this one has a we're going to talk about binding energy in a minute. Okay. Right. So there's energy holding this. There's energy holding this outer shell electron in place. Right. Let's say it's -10. Okay. We won't even know. We don't even need the unit. The unit is electron volts. But let's say the energy holding this in place, the outer one is -10. Okay. And let's say the inner one is -50. Okay. Well then, is -50 a bigger number or a smaller number than -10?
The -50 is a
smaller number, right? Because if you look at the number line, -50 is way further away from 0 than -10 is, right? That's how you think of it. These are all negative numbers. But what's important here is that, let's say this electron, right? Let's just write it. Let's say this outer shell electron has -10, and just to give you the units, we're going to deal with it in a minute, it's keV, kilo electron volts. Okay, so let's say that electron is held in place with that much energy. That's how much energy the nucleus is pulling. If you wanted to remove that electron from the atom completely, you would have to hit it with that much energy. Okay? Good. +10. It doesn't matter if it's positive or negative, but we'll get to that. And let's say this inner shell is held in with -50 keV. Okay? The difference between them, what's the difference between -10 and -50? 40. Not -40, just 40. Okay? So, let's say this electron is ejected from the atom. It's now over here. Okay? Don't worry about how it got ejected. It happened. Okay? We'll talk how it can happen later. But it happened. This electron is gone now. Okay? And just for the purposes of my analogy, let's say this one happens to be able to come down and fill that space. Okay? We said this one's bound with -10 keV, this one's bound with -50. You remove this one, leaving this space open. Okay? If an electron with -10 keV falls into that space and fills up and occupies the space of -50 keV, this electron in this space has too much energy. Okay? How much extra energy does it have? It has 40 keV extra energy. Okay? What's it going to have to do with that energy? It's going to have to lose it, right? It's going to have to convert it, right, into electromagnetic energy. So this guy falls to here, and when it gets here, it'll emit a photon. Now I bet you, if you're listening closely, you can tell me exactly how much energy that photon will have.
40.
40 what? Yes.
keV.
Yep. There you go.
Now,
that's the law of conservation.
From the other thing that's...
Yeah, that electron is just gone. He's going to go meet up with another atom now. We don't care about him anymore. Because he got ejected somehow, and I said it just happened.
The electron is the actual... So it's the pool ball that gets off.
Yep.
But the sound, the crack, is
the photon.
Is the photon.
Yeah. That's a good analogy. Okay. Yeah. Yeah. The pool balls are the electrons, and the sound that they make when they hit is the photon. Yep.
Working.
That's good. I like that analogy. All analogies have their limit, but I like that one. Good. So that's it. That's the trick here in understanding where the other.
Does this have to do with why they want labs before people get like X-rays that have things done with contrast and stuff?
No, not necessarily. Depending on the contrast, it'll change like blood composition, it'll change kidney function and stuff like that. So
yeah.
It's more of like a macro scale that they're worrying about. This is teeny tiny microscopic scale.
Okay.
So no, not in that way. Okay, so electrons can exist in shell levels and only in those shell levels. You are not going to find an electron right there. between shell levels. It's just not gonna happen, right? It can only exist here or here, here or here, here or here. It will not exist in anywhere between those two, okay? Good.
And that's just science that we know, we don't necessarily understand why.
We know that it is the case, and we understand why. Because there's formulas that show that what happens. We know that it is we know that it is a pattern followed by nature, and the pattern appears unbroken. Yeah.
And we don't have a, it just is.
Why will only get you so far. You know, like a little kid goes, well, why is that the case? And you answer the question, and they go, well, why is that the case, right? Eventually, you just tell the little kid, that's it, that's the bottom, okay? Just because I said so, right? This is the because I said so bottom of that. Yeah, yeah. Okay, good. So there are questions. Yeah, exactly. There are questions that just don't have just don't have an explanation. I am looking for my. Where'd it go? Completely lose it? No, I don't want to take yours. 2 seconds here.
That's a good explanation. I think.
Okay. All right, let's move on. Here we go. Next statement. This is a statement that is true at certain levels of understanding, and at higher levels of understanding, you go, why did I ever learn that? Okay, it's true unless you want to go a lot further in physics, then it becomes kind of not true. But atoms are mostly empty space. Okay, that is to say, if the nucleus were the size of a marble and placed on the goal line of a football field, the nearest electron would be 100 yards away, the other end of the football field, and it would be the size of a grain of sand.
Say that again?
So your nucleus of an atom is this pen cap, right? Walk 100 yards away from that pen cap. That will be the position of the nearest electron, not the furthest electron, right? 100 yards away, full football field away, and that electron would be the size of a grain of sand. Tiny, right? At 100 yards away, right? Atoms are not 100 yards big, right? Atoms are 1 angstrom big. Okay, they are 10 to the negative 10 meters big. They are 1/10,000,000th of a meter across, right? Take a meter stick. I've got one. Now, how many pieces can you chop this meter stick up into, like, reasonably? What's the smallest unit that you see on these meter sticks? Centimeters are pretty small. How many centimeters are in this meter stick? You know, centimeter. Centi means 100, right? 100th of a meter.
Thanks.
What's a tenth of a centimeter? A millimeter, right? How many millimeters are in a meter? If you speak Spanish, you already know. Because mil is 1,000, right? So there's 1,000 pieces in this meter, right? There's 1,000 millimeters in this meter stick. So take this meter stick, chop it up into 10 billion pieces, okay? So take each, so 1,000 pieces, take each of them, each millimeter, chop it up into 1,000 pieces. Every single millimeter on here, chop it up into 1,000 pieces. Do it again. Chop it up into 1,000 more pieces. And then do it 10 more times. That's how big an atom is, okay? Teeny tiny, right? There are 10 to the 6, so there's 1,000,000 atoms in every millimeter. Take 1 millimeter on here, right? Take your pinky nail, okay? Your pinky nail is 10 billion atoms wide, 1 centimeter, roughly 10 billion atoms wide, okay? So just trying to give you like a sense of scale here. Atoms are small, right? You're not going to see one with the naked eye. You're not going to see one with a microscope. You can't even see the inside of an atom with an electron microscope, the best microscopes we have, okay? You can see down to the electron shell. That's about as closely as we'll ever be able to see. And it just is the case that that's true, and it will always be true. Regardless of that, though, we still have a pretty good idea of what atoms look like. Even though they're teeny tiny, we still have a good idea of their structure. And I think that's an important Important, discovery, development, however you want to think about it. So, remember we said earlier, you've never touched anything, right? You haven't. Objects seem solid. You appear to touch something because there is a collective negative electrical repulsion between your outer shell electrons, right, and the outer shell electrons on the things that you're touching. Okay, that's the sensation of solidity or touching something. Regardless of what your nervous system's doing, telling you that you touch something, you actually touching something is governed by the electric repulsion of your atoms and the thing's atoms that you're touching. When two atoms approach each other, their outer skin consists of a screen of negatively charged charges created by the electrons moving about. That's important. We don't touch things. We electrically repel other things. All right. Within the nucleus of an atom, there are protons. Those are the important particles right now for our purposes. There's two things in there. There's protons and neutrons. Protons weren't discovered for a while after everything else was discovered because, neutrons were not discovered for a while after all these other discoveries because neutrons were neutrally charged. It was hard to detect them. But protons and electrons were discovered very early on because they have electric charge and they respond to electric charges. Okay? So in the nucleus, there are protons. Every atom has at least one proton in its nucleus. Even the smallest atom that we know about, hydrogen, has at least one proton, or has exactly one proton. The charge, the electric charge of protons, we just say it's +1. Okay, so it's got a charge of 1. Okay, it exactly balances and counteracts the charge of each electron. So that means each electron has a charge of, if protons are +1, electrons have to be -1 if they charges equal and counteract. Okay, balance out. Here's the weird thing. We don't know why this is the case. This just is the case. This is one of these bottom of the barrel kind of answers that you don't have a why for. Electrons and protons, while they have equal and opposite electric charge, they have wildly different masses. A proton is about 2,000 times more massive than an electron. Most of the mass of atoms, the weight of atoms, comes from the protons, not the electrons. But here's the weird part. The mass comes from the protons, but all of the chemical interactions come from the electrons. Okay, so where you get your mass from your protons and neutrons, the stuff in the nucleus, but you get the way the atom behaves with other atoms by the electrons. The number and structure of the electrons is governed by the number of protons in the nucleus. Okay, so there's a connection here, right? But it is weird, and it just kind of is the case, we call it the fine structure constant, that atoms have protons and electrons, and they weigh different amounts. They have different masses, okay? It's actually closer to about 1/1837th or something like that. It's a more accurate number. We just say 2,000 because we like to round up and be sloppy, okay? So protons are 2,000 times more massive than an electron. That's the number you should be familiar with. So we have to have a way of talking about atoms, like specifying one atom as opposed to another, and the way we do this is is in two ways. We can count the mass of the atom, or we can count the atomic number, the number of protons. Let me talk about the mass first. Okay. Recall that in the nucleus of an atom there are protons and neutrons. Protons and neutrons account for the majority of an atom's mass. Remember, protons are much heavier than electrons. The atomic mass unit is count up how many protons are there and how many neutrons are there, and that'll tell me the atomic mass. Okay, one atomic mass unit, 1 AMU, is the weight of one proton. Okay, now I haven't said it yet. Neutrons, which we will talk about, are neutrally charged, and they are just a combination of a proton and an electron. For purposes of just being sloppy and roughly talking about these things, a proton and a neutron weigh about the same. Okay, because a neutron is just a proton that has captured an electron. Okay, and electrons are really small. They weigh almost nothing. Okay, so for our purposes, protons and neutrons weigh the same. Okay? So if you count how many protons and neutrons an atom has, you will know its atomic mass. Okay? The unit is an AMU, and it's the mass of a proton. So if an atom has an atomic mass of 4, how many particles are in its nucleus?
4.
4, absolutely. When I tell you that there's an atomic mass of 4, that means there's 4 particles in the nucleus. Does that tell you how many protons there are? No. It could have 1 proton and 3 neutrons. It could have 2 protons, 2 neutrons. It doesn't, but it could have 4 neutrons, right? When I tell you the atomic mass, I'm just telling you how many particles exist in the nucleus of an atom. I'm not telling you what the mixture of them is, and importantly, I'm not telling you the number of protons, which means I don't know the number of electrons, which means I can't determine the atom's chemical behavior, which means I know precisely, well, almost 0 about the atom. All I know if you tell me the atomic mass is what it weighs, okay? Haven't told you nothing about its behavior, okay? So the number that's more important for our purposes is called the atomic number. It's given as a capital Z, so we call it the Z number. This is important. This is the number of protons in the nucleus. Now, we just learned about the proton. What was special about it?
It's 2,000 times bigger than the electron.
And what's its mass? 1 atomic mass unit, 1 AMU, okay? So it's got a mass of 1 AMU, so that's its mass. What's its charge? 1, plus 1, a proton, plus 1. Pro means positive, okay? So you've told me everything you need to tell me about the proton. You told me how much it weighs and what's its charge. Mass and charge, okay? Physics likes to simplify things. I don't want to know what its hopes and dreams are, right? I just want to know what's its mass and what's its charge, okay? A proton has a mass of 1 and a charge of 1. Easy peasy. Plus 1 to be specific, but 1 implies positive. If you tell me the atomic mass number of an atom, the atomic number, the Z number, I can tell you, and you will be able to eventually tell me how that atom is going to behave chemically. Okay? You're about to learn how it's going to behave chemically, which is really, really cool once you figure it out. And I won't claim to have the only and complete understanding of this, but I've got enough to get you guys where you need to be, I think. Okay, so that's the first thing to learn, is that atoms have protons have a positive charge, and they have a mass of 1, okay? The next thing to learn is, you already know, because I've said it before, and you guys probably have just heard this for your whole lives, opposite charges attract, and like charges repel, okay? So what is equal and opposite in charge to a proton? Neutrons are neutral, so no charge. An electron. So what's the charge of an electron? -1. What's the mass of an electron? You know this. You have everything you need to figure this out. 1/2000th of an AMU. 1/2000th of an atomic mass unit. An atomic mass unit is the weight of 1 proton. Electrons are 2,000 times smaller than a proton. So an electron is 1/2000th of an atomic mass unit. That's its mass. You've just told me the mass of an electron and its charge. You've told me all I need to know. Remember, I don't care about its hopes and dreams. I just want to know what the mass is, what the charge is. Okay? Mass is 1/2000th of an AMU. Charge is -1. Now, here's the cool thing. Opposite charges attract, right? And nature loves it when things are neutral. Nature loves it when things have no overall charge. So an atom sitting by itself, away from the environment, if left alone, it will get to a point where it's neutrally charged and stay that way. Okay? And the atom's happy. Nature's happy when atoms are neutrally charged. Well, what does that mean to be neutrally charged? That means to have the same number of negative and positive charges. Okay, so if you're an atom and you have, let's say, 8, oxygen's got 8, okay? Let's say you're an atom and your Z number is 8. You have 8 protons in your nucleus, you are oxygen, okay? If to be neutrally charged, how many electrons would you grab onto? 8, the exact same number, right? To make an equal and opposite number. So if I know the Z number, I know how many electrons the atom will try to hold on to be neutral. I know how many electrons the atom will have when it's happy. Okay? And with the following rules I'm going to teach you, I'll be able to tell you, and you'll be able to tell me, in what configuration are the electrons. Remember, because we saw them arranged in shells, right? In the previous slides. So I'll be able to tell you, and you'll be able to tell me, what is the arrangement of the electrons, how are they organized, and how does that change the chemical behavior of the electron, of the atom, and the electrons in their positions. Okay, so atoms have a nucleus. In the nucleus are positively charged protons. We haven't talked about the neutrons yet, but the neutrons play literally zero role in the chemical behavior. Okay. Okay. So the Z number determines the chemical identity of the element. If you take an element, oxygen, which has 8 protons in its nucleus, the Z number of 8, take it here, and you can't do this, but just to bear with me, analogy, you pluck out one of its protons. How many? You took away 1 proton from something that had 8, so how many does it have now? It's not oxygen anymore. It's not going to act like oxygen, because now, with only 7 protons, it will only now grab onto 7 other electrons, which means it's going to act differently. Its electron configuration will be different than oxygen's. Okay. By the way, that's called transmutation, when an element loses or gains protons and changes into one or another element above or below itself on the periodic table. The person credited with the laws of periodicity and developing a working periodic table is Dmitry Mendeleev. And I won't go too far into this, but I'll give you the brief basics here. He says the properties of elements are periodic functions of their atomic weight. That's to say, as an atom gets heavier, as you add more and more protons to it, each addition of a proton changes the name of the element. It becomes something different, and that something different will act differently than it used to. Okay, so an atom with 8 protons is going to act differently than an atom with 9 protons. Okay, this is the law of periodicity. You add enough protons, and then you go back to the beginning of how the original ones were acting. Okay, so let me give you an example here. Okay, this is the periodic table, and in fact, so that's big enough. But we can go right over. I can go right over here. Might as well be useful. I'm gonna let you guys turn your heads a little bit. All right. So I'm not gonna do a bunch, but just some super basic stuff. Okay. So the periodic table of the elements. There's different ways to read it. There's columns and rows. I'm gonna teach you about the columns right now. Okay. So going from left to right, you have on the left side, you have, and this is pertaining to the chemical behavior of the atoms. And I will do more than this later, but right now let me give you just the intro. Hydrogen is at the top here, okay? And hydrogen has a Z number of 1. Usually the Z number, and this is iron blown up big. Iron's right here, but they blew it up big to show you. The Z number or atomic number, the number of protons, the number of positive charges, which tells you how the atom will behave chemically, is going to be in the top right. Okay? And then the top left, you'll see the atomic mass. So the atomic mass is counting what's all the stuff, protons and neutrons, how much does it all weigh? Okay? This is counting how many positive charges are in the nucleus, which will determine chemical behavior. All right? Iron's got 26. Hydrogen is the simplest element, and it only has 1. Okay? So what hydrogen is, it's 1 proton with 1 electron in orbit around it. Okay? Hydrogen's only shell of electrons has 1 in it. Okay? All of these, lithium, sodium, potassium, rubidium, cesium, francium, every single one of these in that column will have 1 electron in the outermost shell. Okay? Hydrogen only has 1 shell, so its only shell is its outer shell. All of these have 1 electron in their outer shell. In chemistry, atoms bond chemically with each other based on the number of electrons not in the middle shell, not in the inner shell, but how many electrons are in the outer shell. Okay? And as you go over here, this second column here, every one of these is going to have 2 electrons in the outer shell. Okay, so if I'm having 1 electron in the outer shell, these all behave like elements that have 1 electron in the outer shell, and these all behave like atoms that have 2 electrons in the outer shell. Okay, and it goes like that, increasing as you go over. Okay, so come all the way over here, all the way over here to the far right. Okay, in the far right column, all these ones in blue, these are what are called noble gases. Okay, all these ones over here on the far right, far left was only 1 electron in the outer shell. And on the far right, you have atoms that have completely full outer shells. They're done. And we'll learn here in a little bit how many electrons the outer shells can hold, blah, blah, blah. But right now, let me just tell you, all of these are full. Okay? So if you're an atom of helium, neon, argon, krypton, xenon, or radon, and you bump into another atom, your electron shell is full, and your atom is happy. It doesn't need to make any chemical bonds. Atoms make chemical bonds with each other to gain or borrow electrons so that they can be full. Okay? Hydrogen bonds with oxygen because hydrogen needs to borrow an electron. Okay? Oxygen also needs to borrow 2 electrons. We will talk about that. But all of these ones over here, they don't need to borrow anything from anybody. They got everything they need already. You guys know what we call them? All these guys that don't need to hang out with anybody, they're too good to hang out with you?
Noble gas.
They're called noble gases, okay? They're called noble gases because they're too good for you, okay? They don't want to hang out with any of these other guys. They don't want to make connections with any of these other guys because these guys are fine. They're full already. They don't need your help, okay? They're noble gases, okay? Helium's a great example. Helium, its atomic number is 2 protons in the nucleus. It'll have 2 electrons orbiting around its only shell, and it's full. Okay, and the rest of these are the same case. Okay, and everything in between there. So that's part of learning the periodic table of the elements, is that we call these rows of periodicity. Each one will behave like everything else in that column. Okay, good. I'm going to jump around a little bit.
Do we have to know about the bomb salt?
No, not right now. So here's what you do need to know. You need to know that the atomic number tells you how the atom will behave chemically, okay? And you need to know that there are certain common elements in the body, okay? And you should be able to, after learning the rules that I'm going to tell you in a minute, you should be able to tell me what the electron configuration is. Okay, and we'll get there, don't worry. But let's cover some basic ones, okay? So right at the top, basic stuff. Hydrogen and helium. Hydrogen is far and away the most abundant element in the universe. Something north of, you can look it up to prove me right or wrong, it's something north of 90%. I'm pretty sure it's like 95 or more percent. But anyways, the majority of the universe, the mass in the universe, is hydrogen gas, okay? Well, yeah.
What slide is this?
13. I went back in time. The majority of mass in the universe is hydrogen gas. Why? Because the majority of mass in our universe is in the form of stars. What are stars? Except for they are a collection of hydrogen gas that has collapsed under gravity and began fusing hydrogen atoms together to make helium. That's how big atoms get made. The first atoms, when the universe went poof, when the universe went poof, the Big Bang, the first atoms were hydrogen. Some helium, but hydrogen. Okay, 1 proton, 1 electron. Okay. Now when stars began to form, stars would smash hydrogen and hydrogen atoms together. When 2 hydrogen atoms smash together, they fuse to form helium. That fusion radiates some energy. Some energy escaped from that interaction, and that's how stars light up. Stars fuse hydrogen to helium. That's why hydrogen and helium are the 2 most abundant elements in the universe. Every subsequently larger atom came from fusing, for example, helium together. and forming larger elements, and smashing those elements together, forming even larger elements. And so on and so on. Stars blow up, spread their elements, more stars get created, those stars fuse elements into larger elements. That's where we get the full periodic table. The elements are from stars fusing and then exploding. So star stuff, star stuff, star stuff, star stuff, star stuff. We're all star stuff. Tables and chairs, all of it's star stuff. Okay? Good. Leftover remnants from previous stellar explosions. In our body, the most abundant element in your body is oxygen. Okay? But for structure, you're made of a lot of carbon too. You know, if you know anything about sci-fi, you'll hear things like, we are carbon-based life forms. What the hell does that mean? That means our molecules are built from carbon. Okay? Now, here's what's cool. Remember, everything in a column behaves like the other things in the columns, right?
Right.
Okay, so if you're doing some sci-fi and you go, we're carbon-based, could there be other things like us that aren't based on carbon? Absolutely. Look at carbon, number 6 here. Look right underneath carbon, silicon. Silicon has the same outer shell structure as carbon, okay? Silicon will behave chemically a lot like carbon does, okay? So if you are trying to design, you know, your Elon Musk and you make it to Mars and there's no aliens there, and you're like, I'm gonna make some aliens, right? Then you can in principle build them out of silicon, because silicon behaves like carbon, okay? We're made out of carbon because it just happened to be what the abundant elements were when the soup of life started to kind of get together, but, you know, germanium, tin, lead, all behave chemically like carbon, because they're at the same spot in the periodic table. All right. You should remember the atomic number for each of these. Carbon has 6, oxygen has 8. Now we're getting a little heavier, getting into the metals now. Aluminum. Aluminum is one of the lighter metals, but it's still heavier than the normal stuff. Aluminum has an atomic number of 13. Calcium, super important material for nerve cell conduction, nerve impulse conduction. And calcium's at an atomic number of 20. And let's just go down to the bottom. The heaviest, let me rephrase. The heaviest stable, naturally occurring element is uranium. Anything larger than uranium is either not stable or not naturally occurring. As in, we can make it in a lab, but then it falls apart after we make it. Okay? The largest stable, naturally occurring element, uranium. Lead is the most stable element. Lead is the heaviest stable element. Uranium is heavier, but uranium tends to be radioactive. Okay, we've got these. For use inside the X-ray tube, tungsten's important. Tungsten has a atomic number of 74. Good. You know, pretty much always, I mean, every time you're in my class, you're going to have the periodic table shown right up there. You'll have these at your disposal, but you should work on remembering these, right? You know, I keep random access. I'll keep hydrogen, helium, carbon, oxygen, aluminum, lead, and probably tungsten at, you know, random access to pull out to talk about. But, okay, good. So if you've got tungsten, 74 for its atomic mass, what's that telling you? What's the 74 telling you? It tells you a couple things. What's the first thing it's telling you?
74 electrons? No.
That's what you can infer, but what's it actually telling you? The mass? It's not the atomic mass, it's the atomic number. It's telling you something about the positive charge. 74 protons, right? So let's go over here to tungsten, over here on the periodic table. Where we at? There's tungsten, okay? Tungsten's got an atomic number of 74, right? But if you look at the top left of that one, you'll see that the top left tells you the atomic mass, right? If you can't see this, the atomic mass for tungsten is 183, okay? So how many protons does tungsten have? 74. What's the atomic mass? Good. Someone plug that into their phone real quick. What's 183 minus 74? Anybody got a calculator handy?
Taylor's doing it.
109.
So 183 minus 74 was 109. Good. What's that? The 109. What did I just do? What was the equation? We took the atomic number and subtracted that number from the total mass of the atom. It's telling you not the protons, the neutrons. So electrons are so small, when we talk about mass, they don't account for anything. Because a single electron is at 1/2000th of the mass of a proton. So they're so small, we don't talk about them when we talk about mass. When you talk about the mass of an atom, all you have to tell me is how many protons are in its nucleus, how many neutrons. You do not have to tell me the electrons. Okay? The electrons are so small, where they count for electric charge. Remember I told you that was weird, right? They have the same electric charge as a proton, but their mass is so small, 2,000 times smaller than a proton. So when you tell me about mass, you do not have to count the electrons. Okay? You just don't count the electrons. When you talk about mass of an atom, or anything, you're telling me how many big particles it has in the nucleus. What's the mass of the nucleus, more specifically, okay? So you took 74, which is how many protons it has, and you subtracted that number from 183, which is the total mass, protons and neutrons, okay? When you get the number 109, the 109 is telling me how many neutrons this element has, okay? So where this element tungsten might have 74 protons in its nucleus, it also has 109 neutrons in the nucleus. Now the neutrons, they count for mass, like heaviness, right? But they do not change the chemical properties, okay? I can have an atom of tungsten with 74 protons, but let's make its mass, it's not typically, but let's make its mass 200, okay? It'll still have 74 protons. It will have, if you raise the mass of tungsten, it'll still have 74 protons, it just will have more neutrons now, or less neutrons, okay? So, to be very clear, atomic mass, that number in the top left, is the total number of protons and neutrons on average. The top right is telling you how many protons, okay? That number is fixed. If this number, 74, happens to change, let's say the atom loses a proton because of radioactive decay. Tungsten isn't radioactive, but let's say it is, okay? Tungsten loses a proton. Well, if it loses a proton, its new atomic number is going to be 73, okay? And it'll be tantalum, which I have no idea what the chemical behavior of that is, okay? But we know that if tungsten is, somebody gives tungsten another proton, again, not going to happen, but in abstract analogy land. If somebody gives tungsten another proton, its atomic mass goes up, but the atomic number is going to change from 74 to 75, okay? And now tungsten behaves like rhenium, okay? Rhenium is another metal used in the X-ray tubes, which actually behaves a lot like tungsten, with different heat capacities. But importantly, it's different, right? It's a different thing, okay? That word, again, is called transmutation. When you change the number of protons in an atom from one number to another number, you have transmutated the atom and you've changed it into something different than it was originally, okay?
Question.
Yeah, please.
So, are all jumbles of protons, are they all the same?
Yes.
They're
Yes.
the same stuff?
Yep, same stuff. Every
But
proton is...
But the number of protons will turn it into something different.
Yeah, so, well, let me phrase it like this. Anytime you've got a collection of protons, and there's 8 of them, okay, you have oxygen, right? Anytime you collect 6 protons together, you have carbon, right? Anytime you collect 74 protons in one little bundle, then you have tungsten, okay? This bundle of 74 protons that I call tungsten, somebody else goes out and, again, analogy land, but somebody else goes out and collects 74 protons and sticks them all together and shows it to me, that's also tungsten, okay? Doesn't matter, anytime there are 74 protons in the nucleus of an atom, we get to call that thing tungsten. And if that number changes, it's not tungsten anymore, because it will act differently chemically. So that's what elements are. They're a collection of protons and electrons and neutrons, but importantly, it's the collection of protons that tells you what the atom's going to do, okay? How it's going to act chemically, okay? So what we're about to get to is, how do the electrons arrange themselves based on the number of protons, and that's going to be the important, an important story. So let's get to that.
Okay. And then one last
Yeah, please.
clarification. The total number of protons and neutrons is...
In the nucleus is the atomic mass. So there was two things you should have learned here. Let me go back to the slide. You should have learned two things. You should have learned that there is something called atomic mass, measured by the number of particles in the nucleus. That's going to be on a periodic table, the top left in each thing, in each square. Atomic mass. And secondly, there's the number called the atomic number, the Z number. That's not how many particles, that's how many protons. This will this will determine the identity of the element. Very briefly, because it doesn't matter for radioactivity, or it matters for radioactivity, but it doesn't matter for X-rays. Let's talk about the neutron. So, all right, Rutherford does his experiment in 1911 with his ray gun. He figures out there's a nucleus, but he has no idea what else should be in there. He has, well, maybe he has an idea. He doesn't know for sure. He predicts that there should be something called a neutron. Don't ask exactly how he predicts it, but he predicts it, okay? But he couldn't find it. Why? Because if you're trying to find something that is not electrically active, not electrically responsive, then you can't move it around with electrical charge, okay? You can't detect the neutron by manipulating electric charges. But he predicts it. So here's the neutron. The neutron is in the nucleus of atoms. It has nothing to do with the chemical behavior. It has everything to do with the mass of the atom, though. A neutron's mass is slightly heavier than a proton. For most purposes, most of the time, we just say it's the same. Okay? So if a proton has an atomic mass of 1, a neutron also has an atomic mass of 1. But here's the deal. What a neutron really is, it's electrically neutral. It has no electric charge. That's what the word neutron means, neutral one. Okay, that's the word, the written out definition, neutral one. So it's electrically neutral. It is thought of, and it's sort of true to say, a neutron is a proton and an electron bonded together. Okay, the weak nuclear force has a role to play here. Okay, so the weak force that we kind of like wave our hands and say, yeah, the weak force, don't worry about it. It's doing stuff here. Okay, nothing that we really care too much about, or else I'd spend more time on it. But that's what's happening. You have a proton and an electron bonded together. Call that a neutron. Now, neutrons inside of a nucleus are pretty stable. They tend to kind of stay like they are. Okay, you put them all together in a big bag and they kind of just stay together. Okay. But you take a neutron and pluck it out of a nucleus and hold it out in empty space, you get what's called radioactive decay. Okay? That neutron will fall apart, decay. Okay? When it decays, we say it's unstable, tends to decay. Here's the thing. If a particle is made up of smaller particles, and there can be a dispersion of energy by those particles splitting, then they will tend to split. Okay? If particles can split, then they will tend to split. Okay? Nature likes things to be in their lowest energy states, and if two particles can break apart, and them being broken apart is lower energy than them being together, then they will tend to break apart. Okay? So, a neutron out in empty space will fall apart. Okay? When it falls apart, you have left over a proton and an electron. Because the electron is the lighter of the two particles, the electron is shot away at high speed. We call that beta radiation.
This is going to be like aside from the slides, but are we going to have a lunch today?
We're going to talk and talk and talk, and then I'm going to run out of steam, and I'm going to let you guys go.
Yes.
Yeah. So I am nowhere near the end of this, but I am somewhere near the end of what I'm going to cover today. Okay. Yeah. Yeah, so just you guys do your best to hang in there. You guys are doing great. Thank you. I hope this is helpful in some way. I know some of this is super technical and super difficult and like almost eye rolling sometimes, but we gotta just pull through it, right? We have to. That's the way to get to where we need to go. Okay. You guys okay with that? Neutrons are a proton-electron pair, and they will decay outside of an atom. In fact, some radioactive decay in radioactive atoms is due to these neutrons decaying. Check it out. If a neutron in an atom decays, what would it turn into? A neutron. You see it right here. What does the neutron turn into when it decays?
Turns into a proton.
And an electron, which shoots away from the atom, okay?
Right.
So let's say you have an atom, right?
Oh, shit.
Sorry, I'm speaking. Let's say you have an atom here, okay? Ignore the electrons, right? But let's say you've got a positive, a neutral, another positive, another neutral, okay? This is helium, by the way. Okay, this is one isotope of helium with 4 things in it, okay? What happens? So this is helium. How do we know it's helium?
Because it has 2 neutrons.
2, not neutrons,
Sorry,
2 protons, right? So the atomic number for this, the Z number, is 2 protons, okay? But what would happen if one of the 2 of those neutrons labeled N, what would happen if one of those decayed?
They would fall apart.
So it falls apart.
The charges would be uneven.
Well, hang on, you're getting to the right step here. The neutron falls apart, and what happens when a neutron falls apart? It turns into a and electron and a proton. Now, the electron is shot away at high speed. Don't ask why right now, but it is. Okay? The electron shot away at high speed. The electron's out here. We don't care about the electron anymore. It's gone. It got shot away from the atom. Okay? What's left behind now?
3 protons and 1 neutron.
Right. Is helium, can helium have 3 protons?
No.
Let's go over here. What did it turn into? It turned into lithium, right? Lithium over here behaves like hydrogen. Helium's way over here. Okay? Helium behaves like helium. But we just took helium and through radioactive decay, we turned it into a completely different element. We transmutated it. Okay? We took it from its spot, which is number 2 on the periodic table, top right, and by decaying a neutron, we added a proton. That make sense? We took a neutron, split it apart, and what was left behind was 1 positive charge. Now, is the mass in the nucleus changed?
No.
You're right, let's work it out though. What was the atomic mass when we started?
2.
No, that's the atomic number. What was the atomic mass?
Four.
How many things were in the nucleus total?
4.
4. There's 4 circles in that nucleus, right? Right? Go follow. 2 protons, 2 neutrons, which is what we started with, right? So 4 things. How many things are there now? How many particles are in that nucleus now?
4.
Still 4. Did our atomic mass change? No. We stayed the same. Our atomic mass number stayed the same. What changed?
The amount of
How
protons.
many?
Right, our atomic number changed. The atomic mass was left unchanged, what started at 4, ended at 4, but we changed the atomic number from 2 to 3, completely changing the element. Lithium is not going to act at all like helium, okay? But radioactive decay changed helium into lithium, okay? That's what neutrons can do for us.
So that's why
That's
radiation, that's why tungsten, which you're spinning the dial and playing with it, is not a problem, but when you shoot something at it, it becomes harmful.
I wouldn't think about it like that. I would think about that in atoms, if the number of protons changes, the atom changes. To a different, it acts differently now. That's all I was trying to get across. And neutrons are weird because neutrons can change the number of positive charges. Neutrons decay, they tend to decay. Atoms with more neutrons, let's go up to the big ones, okay?
I'm just bringing it into a practical understanding.
Yeah, I mean,
Just something practical side.
it's, we're gonna talk about radioactive decay later, but let me just briefly,
Okay.
so here's sort of how you should think about this. The larger an atom is, the more likely it is to be unstable. Unstable atoms tend to undergo radioactive decay to gain stability, okay? One of the types of decay is when neutrons decay into proton-electron pairs, okay? So these large atoms, take, let's see. Let's take, where's, 92, you're right here. 92. There's uranium here, okay? Uranium's radioactive, okay? Let's figure out how many neutrons uranium has. Can somebody do that, help me out with this? Uranium has 92 protons, and 238 is its atomic mass. So you would take 238 minus 92. 146? Okay. Which, we figured out that tungsten had 109 on average extra neutrons, okay? Neutrons. Where, one more time the number? 146. Where on average, uranium has 146 neutrons. A lot more, right? So that's how atoms get massive. Atoms don't get massive by adding on protons. Atoms get massive by adding on neutrons, okay? These larger atoms tend to have a larger occurrence of neutrons, and the large number of neutrons, because neutrons are unstable, tends to make decay happen. When decay happens, atoms can actually go up on the periodic table. They can change their atomic number upward rather than downward, okay? That's almost a side note, because this does not have any effect on the production of X-rays initially. All right, so the last thing I need to teach you for today, all I'm going to get to for today, is we're going to learn how electrons arrange themselves. Okay, so we learned how atoms are structured. There's a nucleus with protons and neutrons. We can count the number of total things in the nucleus, protons and neutrons, or we can count just the protons. You count just the protons, you're telling me the atomic number, the Z number. When you tell me that number, Z number, you're telling me how many electrons that atom will want to hang on to. Okay? Once you know that, we need to then figure out in what arrangement will those electrons be. That will determine the chemical properties. All right, so let's do this. Let me briefly pause.